What is the Cosserat Continuum? Earth's crust is dissected by thousands of tectonic faults. These are especially abundant near the tectonic plate boundaries. Faults are surfaces in the rock mass, which split the rock volume into two blocks. Under the influence of tectonic forces, these two blocks slide along each other, producing characteristic slick lines. Faults in the Earth's crust are not chaotically distributed. In contrast, they form highly organized systems. Observations by structural geologists show that faults tend to grow in such a way that they form groups of parallel or subparallel fault sets. A group of fault sets with different directions is called a fault system. One of the most commonly observed fault systems is the conjugate fault system. This is composed of two sets having the conjugate symmetry with respect to the direction of compression and extension. Near the tectonic plate boundaries, forces acting on the rock cause slip along multiple faults. This leads to deformation of the crust, which is being contracted in one direction, and extended in the perpendicular direction to contraction. Based on the observations of crustal deformation, structural geologists also discovered that faults accommodate significant rotations of blocks between the fault planes. This photo illustrates one example of such rotations in Slovenia. Originally, the limestone megabed was deposited in an approximately horizontal position, but was later rotated along a series of faults composing a fault set. Such rotations are often called the domino-type rotations or bookshelf rotations, and can be described effectively within the framework of the Cosserat continuum theory. The Cosserat theory, or also the micropolar theory, was proposed systematically by the Cosserat brothers at the beginning of the 20th century. A revival of this theory took place in the subsequent decades, describing elasticity, hyperelasticity, and viscoelasticity. Today, the Cosserat continuum provides a relevant description of the mechanical behavior of several classes of materials with microstructure, such as liquid crystals, rocks, granular media, cellular solids, composites, dislocated crystals, and faulting-related deformation of the Earth's crust. Classically, the deformation of the rocks due to faulting is described based on the Cauchy continuum theory by introducing a single vector field, called the displacement vector field. This describes the process of an arbitrary point being displaced due to a slip along the faults. Consequently, the classical mathematical quantities that describe such deformation are deformation gradient tensor U, and macro rotation tensor Wm. The deformation gradient tensor describes in which directions the rock is maximally contracted and extended. These are so-called principal strain directions, λ1, λ2, and λ3. Macro rotation tensor describes how the entire region is rotated for some angle phi, m, due to slip along a multiplicity of faults. The Cosserat continuum theory introduces an additional vector field, called the Cosserat micro-rotation field. This describes the rotation of individual blocks of rocks between the fault planes. Consequently, there are two rotations in the Cosserat continuum, A, the macro-rotation, and B, the micro-rotation. The difference between them is called the relative micro-rotation phi, r. The micro-rotations within the Cosserat continuum may vary from place to place, which leads to torsion and curvature of the rocks. This is described by the torsion curvature tensor kappa. The deformation of the Cosserat continuum is thus described by the deformation gradient tensor U, the torsion curvature tensor kappa, and micro-rotation tensor Wc. The associated stress measures are the stress tensor sigma and the couple stress tensor mu. There is not just stress in the Earth's crust, but also the couple stress. The classical seismology failed to solve the earthquake forecasting problem, because it completely ignored the effects of the couple stresses. In contrast, the omega theory showed that the couple stresses play a major role in earthquake triggering and seismic reactivation of tectonic faults. As such, the Cosserat theory forms a foundation for the omega theory and the Quantectum earthquake forecasting system that represents a user-friendly application of these complex physical processes in the Earth's crust.